that have this conformation to represent different kinds of parts of them. This is a simulated protein. We can see some folds and some bonds that compose this toxic protein for snake. This is our more or less preliminary results. We can see the structure and dynamic properties of this protein. If you see, this is an experimentation at 2 temperatures. In general terms, some people work with only 1 temperature, but now we try to work with different kinds of temperature to see the structure of these proteins. And you see in red is 15 degrees and in green is 30 degrees. Yeah, you can see some type of results here, similar here, similar here. But in these zones, we have a switch with respect to this in the same magnitude. Yeah, and this is our results of RMS-CIF, and we see some large peaks that we try to explain that they are the disulfide bonds that we show in the previous analyses. Well, this is another results in the scorpion. If you see, this is again the alphas, betas, helix, and this is a movie of yeah. So okay. This is our results of this simulation. All bridge. There are constant along the time of simulation. We suppose that this is that they have the high toxicity for this type of proteins. Okay, this is one, and this is another. This is exclusive of Mexico. Another one is exclusive for North America. And then you see again the alphas, helix, betas, and disulfide ones. They have a big structure. The structure is maintained. And this is for South America. We try to think that the different species of animals have a different types of venom, but this shows that it is very similar in all this range of distribution. Yeah, again, we can see the disulfide bonds and the same structure. Okay, and what are our future work? Well, we stay working about the Markov states models. This is the same protein with one time, 2 or 3 and 4 times of simulations. And if you see this, the structure of our protein that we work and all the structure that we stay working now. This is an example for this protein with PDB-ID from a scorpion. Well, we have some projects, Roberto and I, and we have some estatal and federal support for stay here, and well, to all our students and people that works in our labs. Okay, thank you.
so much, Felipe. Any questions? Okay. So I have a question.
Yeah.
What is the target of these venom proteins? Is it known?
The target?
What does it interact with?
Well, we use mainly the proteins that we see in the PDB, and when we simulate them, we see the bonds and the disulfide bonds that are the target that we simulate for perform this analysis. The targets are the disulfide bonds that we see in all toxic proteins that we work today.
Okay.
Do you think that this disulfide bond could be also into residues that would interact with the calcium channel, for instance, to promote the toxic effect or the myotoxic effect? Or it's just the structure of the effect?
No, I think that this promotes the toxic effect because the loops are in contact with the membranes. Well, it's a theoretical hypothesis. And then these loops after changing the channels for sodium and potassium, but the toxicity are in these bonds, these sulfide bonds. I think because like you see in different kind of species, the venom is similar with these sulfide bonds. If we work with a docking or something about over these sulfide bonds, maybe we can change the toxicity.
I mean, because the 3P1 structure that recently appeared, this calcium channel, has the double knot toxin bound to the extracellular site,
Yeah.
which is the spider toxin. So probably it's like the way to act. But I don't know. Maybe also it could be permeabilizing the membrane in some way and triggering the channel by side or by a lateral effect.
Yeah, well, this is a cascade of events. Some proteins act first and promotes lysis, and then another proteins in the same venom act in the channels or in the movement of these proteins along the system. But this one is only one from each species, for the 52 or more proteins from each compound.
Okay. Great. So let's thank Felipe and the lessons.
Yeah.